Hi, I'm Adam Mallette from Dr. Jeffrey Reimer's group at the University of Houston. I'm going to be sharing our multi-directional approach to understanding and controlling zeolite crystallization. So zeolites are naturally and synthetically forming aluminosilicate crystals with channels and cages that give it molecular sieving capabilities, and its aluminum sites give the framework a negative charge. And so these Bronsted acid sites are critical for applications like separations and catalysis. So tuning the silicon to aluminum ratio is critical for being able to control zeolite properties. Another way to control zeolite properties is by incorporating metals into the framework instead of aluminum. So for example, Professor Davis and others have shown that tin can be incorporated into zeolite beta and enhance its performance in glucose isomerization. So now we've also started looking into metalloaluminosilicates, which are bifunctional zeolitic materials with both Bronsted and Lewis acidity. So combined with shape selectivity, these materials offer an enormous potential, but we cannot really control their composition because we don't have a good fundamental understanding of zeolite crystallization mechanisms. So recently there's also been additional pressure to understand zeolite crystallization because of nuclear waste. So how are these related? Well, the nuclear waste is going to be vitrified in glass form and then stored underground. But studies have shown that zeolite GIS will nucleate at the surface of the glass and actually accelerate its degradation. So we want to suppress zeolite nucleation to stabilize the waste glass. So this has inspired us to pursue a novel multi-directional approach where we add multivalent metals to the zeolite growth solutions in hopes of finding ways to suppress zeolite nucleation. And then from these studies, we've gained molecular insight into how to better rationally design zeolites. So why are we looking at multivalent metals? Well, previous studies have demonstrated that tin can dramatically suppress zeolite crystallization rates. And then furthermore, here's an example nuclear waste glass composition. You can see that there are plenty of multivalent metals in the glass. So we want to identify which of these can most effectively suppress zeolite crystallization. So we looked at a large number of different multivalent metals and methodically studied which of these can suppress zeolite GIS crystallization rates. So typically, GIS forms via a stepwise process known as the Ostwald rule of stages, wherein we have an amorphous material that converts to crystalline phagosite, which is a very important industrial zeolite that accounts for over 95% of zeolites used commercially. And then phagosite will undergo interzeolite conversion to GIS. So by identifying the extent of this conversion from phagosite to GIS, we can determine the effect of any of these metals on GIS nucleation rates. So when we have alkaline earth metals over here, we see that because GIS still forms, they're really not having much of an effect on suppressing the crystallization rates. However, when we add transition metals, most especially zinc, tin, and indium, we see that we can completely suppress GIS formation. And in fact, where it would typically form in 4 days, GIS doesn't even occur for more than 4 weeks. So another interesting insight from this study is that it highlights the differences between the forms of metals take when they're in solution. So on the left, we have alkaline earth cations, which form divalent cations. But on the other hand, a lot of these transition metals will form anionic metal hydroxide complexes. And this is really important because this is the same type of form that aluminate species will take in solution, which will typically bind with silica and then nucleate to eventually form a zeolite. So what we effectively have is that these metals are competing with aluminum to bind with silicon in solution. And we know from previous studies that zinc will win out in this tug of war over aluminum. And we think this holds the key to understanding why some of these transition metals are suppressing zeolite nucleation rates. Basically, we have zinc sequestering silicon in solution, forming oligomers that are less amenable to zeolite nucleation than aluminosilicates. So for the rest of this presentation, I'm going to be talking about how our studies of zinco-aluminosilicate systems have given us mechanistic insight into how we can manipulate kinetic pathways, elucidate crystallization mechanisms, and actually tune the physicochemical properties of the zeolites that we have in these systems. So first, let me talk just briefly a little bit more about our control system when we don't add zinc. Basically what happens is pure phagosite will form in 4 hours, and then within 4 days, this will convert to GIS. However, you can see that GIS will start to form in under 1 day. And this is important for industrial syntheses where GIS will commonly form as an impurity and ruin batches of phagosite. So in hopes of suppressing GIS, we identified how much zinc we need in solution to suppress GIS crystallization. So what we see is that by tuning the amount of zinc in the growth solution, we can actually control the phase purity that we get in zeolite syntheses. Unfortunately, this also suppressed phagosite crystallization. So we asked ourselves if there was any way that we could add zinc and suppress GIS while not having any effect on phagosite. And what we found is that there actually is. If we add zinc mid-synthesis, you can see that pretty much immediately after we add zinc, it suppresses any further interzeolite conversion to GIS. And if we add zinc even right after phagosite will form, we never see any pure GIS or any interzeolite conversion whatsoever. So before we get into why this happens, we first wanted to look at a little bit more thoroughly how prevalent this phenomenon is. So my predecessor studied GIS crystallization, and what we have here is a kinetic ternary phase diagram that shows what kinds of growth compositions favor GIS formation. And we can see that in sodium systems at 100 degrees Celsius, GIS will typically form in the silicon-rich region of the phase diagram. However, under the same conditions when we add zinc, you can see that GIS does not form at all, and instead we get one of two metastable states, phagosite and LTA, which are both industrially significant zeolites. So why does this happen? Why does zinc suppress GIS? Well, just remember we have an amorphous solution, and that converts to phagosite, which will then later convert to GIS. And we know that in this phagosite solution in the middle, we have zinc both present in the solid and in the solution phases. So we know it's possible that zinc could be suppressing GIS from either one of those phases. But as I said earlier, our hypothesis is that zinc is competing with aluminum to bind silicon and therefore sequestering the silicon so that it can't nucleate GIS. But it's also possible that instead of this occurring in the solution, we have zinc on the phagosite solid that is preventing GIS from nucleating. We know that zinc is on the surface of the phagosite, and I'll get into that a little bit later. So it's possible that this could be acting as a shell that sort of prevents phagosite dissolving, which would help provide nutrients to the GIS crystals. Or on the other hand, GIS could epitaxially grow on the surface of the phagosite. So of these three possibilities, our hypothesis and these two alternatives, understanding what's happening will give us a clear idea of how the interzeolite conversion from phagosite to GIS happens. So first we did dynamic light scattering on zeolites with and without zinc, and we see that there are no significant differences between the dissolution rates of these two zeolites. So this tells us that the zinc is not preventing nutrients from getting into solution and helping GIS grow. But how do we study whether or not zinc is preventing any epitaxial growth? Well, we did two syntheses with and without zinc. We synthesized phagosite, and then we separated the solid from the supernatant and resuspended each solid in the opposite supernatant. So then after we synthesize these further, we see that when zinc is present in the supernatant, we do not see any conversion to GIS, but we do when zinc is present only in the solid. So this gives us a better idea that it's probably the zinc in a solution that's preventing GIS from forming. And then to do one final study on this, we took the phagosite supernatant without zinc. We recreated this and we found that by synthesizing just that supernatant, we can form GIS without any phagosite intermediate. So this shows pretty conclusively that GIS does not require a phagosite intermediate to actually form. And then of course, when we add zinc to this, it suppresses any GIS and we get instead an amorphous material. So by showing that zinc is not preventing any zeolite dissolution or epitaxial growth, we have a pretty good idea that the zinc in solution is sequestering silicon from aluminum and preventing zeolite nucleation in that manner. So the impact of this study is twofold. First, it gives us a good idea that we need to identify soluble transition metals which will be effective at suppressing zeolite nucleation and stabilize nuclear waste glass. Second, recent studies have actually demonstrated that GIS is very effective at direct air capture of carbon dioxide. So it's growing in relevance, and understanding its mechanistic growth processes will be very important in better designing GIS, because we know it can capture carbon dioxide out of both nitrogen and methane atmospheres. So switching gears for this last portion, I just want to talk a little bit more about acid sites, because these acid sites are very critical, because we know this is where both the zeolite activity for catalysis and its deactivation can both occur. So controlling where the acid sites are located is very critical for determining zeolite effectiveness. So there's a few ways we can do this. One is known as aluminum or silicon zoning, where we have a disproportionately large number of aluminum sites, either at the surface or the bulk. Another is core shell zeolites, where we passivate the surface with a layer of pure siliceous zeolite, and this prevents any undesired surface reactions. We can have paired aluminum sites, which will stabilize either reactants or reaction intermediates. And then, as I've already discussed, we can have bifunctional aluminosilicates with metals, such as gallium, zinc, or tin located in them, and this will enhance zeolite performance. So to figure out how this affects our zeolites, we had to first know where the zinc is even located. From EDS studies, we know that without zinc, we have a homogeneous phagosite crystal. However, when we add zinc, we see that the surface becomes aluminum poor and instead rich in zinc. And our collaborators did DFT studies to show that the zinc will more preferentially substitute into the framework of phagosite at the surface as opposed to the bulk. And they show that this is because zinc will more readily adopt a 3-coordinated speciation rather than 4-coordinated, which favors either surface or defect sites. And then finally, we did XF studies to show that the zinc is indeed in the framework of the phagosite, and it forms a coordination with 3 silicon atoms. So we do have basically a zoned zeolite with zinc-rich surface and an aluminum-rich core. And in future studies, we're hoping to identify any potential applications for this sort of material. So in conclusion, we've used this multi-directional approach to understanding zeolite crystallization. And we've shown that anionic metal hydroxides can suppress zeolite nucleation by sequestering silica from solution. Using zinc has given us a tunable control of the phagosite to GIS interzeolite conversion, even when zinc is added mid-synthesis. We've confirmed that GIS nucleates from the solution phase rather than epitaxially growing from phagosite. And we've demonstrated that it's possible to actually alter the nature of the acid sites in phagosite simply by adding zinc to the synthesis mixture. So it's my hope that you agree that there's an immense potential here for improving zeolite performance if we can just find better techniques to rationally design their crystallization. So with that, I'd like to thank our partners, our collaborators, our funding sources, especially Professor Mormpakis from the University of Pittsburgh, Drs. Niwe and Mokuri from PNNL. I'd like to thank Dr. Reimer and the Reimer Group for all of your support and advice. And thank you for listening. So please feel free to send me any questions in the chat or contact me by email. Thank you.